Yeah, Dave, we're really happy to have you here. We so the kind of the whole thing behind all this was Dave's book Left Brain Left Brain was very difficult to get for a very long time. And people were selling it for lots and lots of money on the internet. And I had a few friends who got it and they spent the money on it. And then I just happened across Dave's website and I found out that he's been selling it for $55 the whole time. So I got myself a copy and I made I made an Instagram post about it. And everybody, I guess, flocked and bought a bunch of them. So Dave and I became friends on Facebook and we started talking and now we're here today. So Dave, why don't you tell us a little bit about you?
Well, I became interested in ukuleles quite a long time ago. And I will cheerfully admit that I have a voice like a frog. So singing was not the high point, but after a few beers, sounded at least better to myself in terms of playing and things like that. And we moved around a lot. But when we ended up in Houston, and I was working for Shell Oil in their research labs there, my wife joined a Hawaiian club. And I decided that probably it was time to begin to learn how to make ukuleles. And so there at that time, and this is in the early 90s, there wasn't much material available in terms of guitar making or ukulele making literature. So I also began to take old ukuleles and repair them. So that helped a lot in terms of figuring out the mistakes that the builders had made initially. So then there was, I think, Stone's classical guitar making book. And then there was a steel string guitar making book, whose author name, unfortunately, I have forgotten at the moment. But we were boiling sides and doing all kinds of horrible things like that to try to put a box together, for God's sake, you know? And so I probably in Houston made, I don't know, 100 or 200 small, the soprano size instruments. And then we moved and eventually ended up back in Hilo, Hawaii, where my wife is from. And I started to try to make a living at both repairing and building. And after about a year, my brother-in-law helped me to get a website. And let's see, how can I reverse the picture? Yeah, I got
it. There you go.
I think.
Yep, we're seeing your desk now. And now we're seeing you. And that's your desk.
Okay.
There we go.
So there is the infamous ukuleles.com website. And it's counterintuitive, but interestingly enough, I just started the first set of pages by trying to do things about string tensions and instrument sizes and stuff like that. And then came across this fact, which is basically it's string pull on the vertical axis and lower bout area on the horizontal axis. And if you go between the soprano ukulele on the left is the smallest and the 6-string classical guitar on the upper right, there's almost a linear relationship between the smallest and the large in terms of string pull per unit area. So then I thought, well, so then probably the physics and engineering are the same for all of these instruments, but it's just a matter of scale. And gradually, that's how the book came about, really, was to try to make a general model for what I would call the guitar family instruments, and by that I mean nylon stringed instruments. And although steel string guitars could be included in this as well, my primary focus is on nylon stringed instruments. Okay. And with all of those instruments, the same sorts of things happen. And this is just the side view. When you string up the instrument, the neck comes up to some extent. The top goes down in front of the sound hole and up behind the bridge. This is not, breaking new ground. It's just what happens. Okay. But what I wanted to try to do was, and this is in chapter 2 of the book. Get out of here now. In chapter 2 of the book, what I wanted to do is basically have an overview of some issues about building guitars. And again, it's nothing really new here. It's just a kind of a recapitulation and a forward-looking view of what the major portion of the book is going to be about. So what size instrument do you want to make? The scale length and the types of strings that you're going to put on there, the dimensions of the instrument, what kind of bracing patterns you're going to use, the stiffness of the top, worrying about dead spots on the fingerboard, the neck and the fretboard dimensions and physical properties, and finally, the effects of temperature and humidity on the whole business. So then, really, and that now beginning in chapter 3 and chapter 4, what I wanted to try to do was build a top deflection model. Okay. And so to do that, we had to first, as an interjection, I should say that I went a little wild with the spreadsheets. Okay. I hate the idea of just writing something with equations and saying, well, and then the author caused it to be done, So there's about 70 different spreadsheets that are included with the book. And almost each time I have a particular equation or an example of something, there's a spreadsheet that comes with the book that will allow you to actually put in your own numbers or shift values for your own circumstance so that you can actually, well, if not quickly, at least eventually get a sense of how to vary different things in terms of the parameters and stuff and move forward for your project, for your instrument. Okay. So calculating string tension, then we needed to work on the torque for the bridge. And basically it's as though the strings were attached to the top of the saddle. So you have a lever, okay? And I'm not clever enough to do the proofs on this, but fortunately, as I have told many people, you don't need to be smart if you know smart people, okay? And so I was very fortunate to have a friend of mine, a physicist named Brent Gallagher, and another friend, Pete Leasis, who was an engineer. And they both looked at the problem and came up with actually exactly the same results by 2 different ways, which is really cool. Okay. Yeah. And so now we have a sense of the torquing force on the top. Okay, we have this lever that's pushing down in the front and up in the back. So then after that, we need to work on the wood properties. And, let me be the very first to say that hundreds, if not thousands, of really wonderful guitars have been made by people who use the kind of touchy-feely or aesthetic approach, and it works for them. Okay. But I can't do that. Okay, I need numbers and measuring physical things and see if that works. And so what we do by not being able to listen to a tap tone, we actually go and measure the physical properties of the wood. And then we measure or calculate the properties of a plate with different braces on it, how the height and the width and the structure of the braces, even composite braces. We can calculate all of that stuff. And in fact, I have, unsurprisingly, spreadsheets which do that. Okay. And when we measure all these physical properties, which some folks can do intuitively, but in fact, what I need to get numbers. We measure things like Young's modulus, which is the inherent stiffness of the wood, both parallel to grain and across grain, and a combination of the two, the twisting method. And we slowly come through and develop a kind of deflection model. Now, what this is all heading toward is measuring top deflections, okay? We know that the top is going to deform under the torque of the strings and the bridge. But it would be great if we knew simply how stiff we needed to make the top to both resist at some level that torquing force, and yet be light enough and responsive enough so that the instrument wasn't basically a hollow body acoustic, okay? And so this whole thing really is heading toward a compliance testing or a stiffness map making for the top of the instrument. Having said that, we have a couple of things that we need to consider. First of all, we need a really simple way of measuring the stiffness of the top. And if you were to go to my website.
Here, I'll put it up for you, Dave. Hold on one sec.
That'd be great. Thank you.
This work? You see my screen?
Yes, perfect. So this is the assemble compliance jig. Now, there are those who say, well, it takes, $10,000 worth of electronics equipment and a huge lab and everything else. I put this together for about $15. And that included the price of the dial indicator. And we need to go back a little bit to the Journal of Guitar Acoustics. And there is a group of papers in there called the Chicago Papers. And in there was an article by Bartolini and Bartolini. And they introduced, I think, for the first time, the idea of measuring top compliance. What's compliance? Well, basically, if you put a load on a particular spot of the top and you measure the deflection, that you're measuring that compliance or the stiffness of that single point. Okay, very cool. And as usual, I looked at the article and didn't think about it anymore after that, but another guitar maker who's I mentioned in the article here pointed out to me that he had been looking at old guitars made by famous makers and making maps of them, and it had helped him in his building. Very cool. So then I kind of went back and I thought, well, we can do this the simple way or the fancy way. Okay. The fancy way is me taking all my equations and making a predictive model, which I did, based on the physical characteristics of the wood, the size of the instrument, and everything else. But also, you can take this simple compliance measuring device, okay, and take an instrument which is already, in your view, successful. And then you measure the compliance map with the string tension off, the strings not under tension. And you have a map of stiffness of the top that was successful in terms of not turning into an ashtray in 6 months, but still being light enough and responsive enough to make an instrument that you like. So if you wanted to make another instrument similar to that, you could actually go in and copy the bracing structure, copy the back, and so forth and so on. And at least in terms of the top, carve the braces until they made a map similar to the successful instrument. Now, you might still have issues in terms of the different frequencies and things and dead spots and so forth and so on, but you would know that the instrument wasn't going to crater and that would be pretty successful at some level. So this is just a way of thinking about these top compliances. Now, if we go back and take a look at the picture I showed earlier off the website.
Which one was that?
The one it's showing two half bodies.
What?
Close the website.
Okay.
Please.
Yep. Perfect. There we go.
Now, what's important about this picture is that it looks at a couple of different circumstances. Okay. On the left side, we're looking at a compliance map, and the numbers are in mils, thousandths of an inch, and they're my predicted deflections for a particular size instrument. So this would be a tenor ukulele, for example, using nylon strings. Okay, so these are relatively low tension strings. And because they're low tension, that would mean that the torque on the top is going to be less. Okay, and so you could have a map which had larger deflections, both in front of and behind the bridge, and still have it be successful in the sense that it wouldn't crater and it would be light and responsive to those strings. But of course, the reality is, once the instrument leaves the shop, you have no idea what the person is going to do with it. And they usually don't follow the instructions. So in this case, the map on the right is using the strings that I actually sent my instruments out with, and that is the Savaret Alliance classical guitar strings, which are higher tension. So if they're higher tension, what that then means is that the torque on the top will be higher, and in this case, it looks like several times higher, and that means that the deflection map for this, quote, successful instrument will have to be quite different than the low tension string map. So now here we have mil deflections in the range of 5 to 7 mils as compared with 15 to 17 mils. Okay. So it's really important in the sense that when you make these maps and things like that, when you look at an earlier instrument that worked for you, you need to think about not just the top, but the strings and the string tension, and therefore, and the saddle height. So that means the torque is going to be different. Okay. You need to think about the wood that you're going to be using and the bracing pattern that you're going to be using. I mean, all this is obvious. Okay. But I see different models out there where bracing really isn't talked about very much. I mean, they make a single deflection measurement on the bridge to talk about instrument quality. And I really feel that the compliance map approach is something, it's not a silver bullet, but it really is a powerful tool, one tool that will help you do a better job of making a better instrument. Yeah. It's, from my point of view, there's kind of three things to put together an instrument, okay? There's carpentry, which is really important, okay? In other words, doing a workmanlike job of fitting the different parts together, and usually making sure that anytime you join two things together, you have another piece of wood behind it to make sure the joint is stable. And then there's this aesthetics, which has to do with the wood pattern, the instrument design, the finish, and things like that. And finally, there's optimization. And optimization really is building the guitar or the ukulele right to that level where it's going to last for a long time. And when it's broken in, be really, really great. Okay. And that's why people are talking about trying to adjust the frequencies so that they land between fretted notes and things like that and so forth. Or they're tuning the top to, or the air resonance to a particular frequency and things like that. But I feel very strongly that measuring the top compliance, because it's such a simple way to do things, can be a really powerful tool in terms of both optimization and instrument response, okay, and longevity. Okay, I don't mind taking a few questions at this point.
So you're going in and with this map, you're checking deflection in multiple places, not just in the area around the bridge. So that has to do with, because in your model, I think it was in chapter 4, you had different holes in the jig that you made, and you were moving the location that you were applying the torque to. So that's where you're mapping these areas. Is that what I'm getting? Okay, cool.
And that instrument that you showed on the website, there's 3 or 4 different pages there, sequential pages. One shows how to make the instrument. Another one shows how to do the measurements. And another one then shows the map.
Okay. Yeah. So you're going in and basically with it, because for those of you who have the book, on page 22, there's like kind of a mock-up of the instrument that Dave was using to kind of check these. I mean, on the website, there's also the instrument there, but you could check different locations between, and you're measuring the radius of between the lower bout and the bridge, right? Is where you're doing a lot of these measurements.
Yes, if you take a look at the little picture,
yeah,
you can see basically, well, you can do plenty or you can do just a little bit of these measurements. And I think with experience, you know when to make a lot and when to make just a few. I mean, if you're going to make a large instrument, large to me is like a classical guitar. I mean, for me, it's like working on an aircraft carrier compared to an ukulele, okay? But I would make at least 2 or 3 concentric rows of measurements around the bridge, okay?
Okay.
And you should kind of do this probably with the bridge double stick taped on, because the bridge is a brace. I mean, we get that, okay? And the bridge plate is a brace also, okay? And I'm assuming that everyone is going to make a top that has like a 30-foot radius, because that radius is free stiffness. It's stiffness that has no weight.
Yeah.
Right. And so my goal, for example, in making an instrument with that compliance map and with that radius is that when the instrument is strung up, the geometry of between the bridge and the lower brace below the sound hole is either flat or still slightly convex.
Okay.
If you begin with a flat top, you end up with it concave. You cannot help it.
Yeah.
And an instrument can still sound good, but aesthetically, it's a little, I'm really not liking it, because it's ugly.
Yeah. Yeah. And so the other thing is all these measurements were taken with either the top on attached to the sides or in some sort of jig that's supporting that top, like kind of somewhat putting not really a load, but you're kind of making this coupled system. So when you're taking these measurements of deflection, you have this top either glued to sides, or in the book you use like a PVC tube, right? Is that right?
Well, the PVC tube thing was really just an exercise, basically, in trying to take a look at deflections under torque in various sets of circumstances. And because I couldn't really what I did to imitate the strings was simply put a dowel in the center of the bridge, and then put a weight on the end of the dowel at a certain distance so that I could actually equal the torque of the strings on the bridge, and then measure the deflections with different weights to get a sense of, to be able to put different torques in and predict the different deflections. I mean, it was an interesting exercise, okay? But the reality of things for an instrument is I would glue the top to the sides, and then with little wedges around the bottom edges of the sides, make it so that the whole setup wouldn't wobble or wiggle when I made deflection measurements. And then I would go in with a little device and a weight and make a little map.
Okay.
So the top is always really fixed to the sides during the building process, but the back is not on yet.
Okay, cool. Anybody else have any questions before we move on?
There are many things I don't know, but I have no secrets. Okay.
Oh, Bo Hannum's got a question.
Yeah, I just bought your book about 10 minutes ago, David. I've watching it, I just dropped. I just couldn't help myself. So, and thanks for talking. With the top deflection on ukuleles, like a tenor uke, how many thousandths? And I'll know this when I get the book. But how many thousandths are we talking? Like 2 thou or 5 thou? Or
it depends on
that's a great question. Okay, and if you take a look at this little picture below, okay, that gives you a sense of the tenor ukulele with 2 different string tensions. And with a low string tension, like just regular nylon strings, the mills could be between 15 and 17 mil. Okay, it's a lot. Okay, it's a very, very easy measurement. And even with the high tension strings, and that would be the little figure on the right, it's 5 or 6 mils. So let me give you a sense of holy smokes, how do I possibly do this? Well, when you first start out in the bridges and the braces are all too big, I have this little 2-pound weight that I put on there, and it moves maybe 1 or 2 mils. That's all. The top really is, it's a brick, okay? And then gradually, and you begin thinning the outer braces a little bit at a time, and you have to really go slowly when you're working on the braces, okay? And measure constantly, okay? And because all of a sudden, you're going to be thinning and getting 1 or 2 mil, and thinning and getting 1 or 2 mil, and all of a sudden you're going to get 3 or 4 mil with a change that you didn't really think was very much, okay? But remember, stiffness of the braces goes as the cube of the height, right? Yeah. And so if you just take a little bit off the top of the brace, depending how you do it, suddenly there's that little break point where it really matters in terms of the top stiffness. So, yeah, going slowly, at least the first few times until you get a sense of how much you kind of need to take off before you actually see some sort of change. Yeah. But it usually goes, like I said, from 1 or 2 mil to 5 or 6 mil for the high tension string But you do need to do the string torque measurements first. When you get the book, you'll end up seeing at the very end, there's a spreadsheet, unsurprisingly, another spreadsheet, okay, that is my predictive model. Okay, and in the model, you need the diameter of the instrument, you need the torque, you need what is called the average Young's modulus for the top, which is, it takes a very, very simple jig to measure, okay? And let's see, what else? Top thickness. And what it does is it creates a series of top deflection estimates for you to use as a jumping off point for making your compliance map. I mean, when you get the book, if you start to use it and you have questions about the spreadsheet, just email me.
You mentioned that there's a linear relationship between the width of the lower bout or the area and the string tension. Does that carry on? I think you went from soprano to classical guitar. Does that carry on from the smaller parlor guitars to dreadnoughts?
Well, this is a string tension. This is a nylon string world.
Okay.
Okay. And if you're dealing with other ukuleles, I mean, it's very common in Hawaii to have both 6 and 8 string tenor ukuleles. And of course, all of a sudden, this total string pull has kind of, gone off the charts in terms of just the normal, what I would call a 4-string soprano concert and baritone. And that's what you can see are these two points here. So probably if you were going to try and do a steel stringed instrument, you could do it, I think. Okay. But your top deflections would be much, much less because the bracing would have to be much greater. Does that making any sense at all? You can just say no.
Yeah. Or how you phrased it, a radiused top is free stiffness. I've not thought of it that way, but it's really well put.
Yeah, for simple nylon stringed instruments, is this whole family, the string pull and the unit area, it's actually a remarkably, well, at least even approximately linear relationship. So you have the same string pull per unit area of the top, regardless of the instrument size, except when you have the multiple string, the pairs of stuff there. So, and that in my mind made it that why not make a model that fits everything from the soprano ukulele all the way through the classical guitar, because really the engineering and the physics is the same. It's just a matter of scale. I don't know.
Did you find any historical literature that showed that, the original engineers kind of mapped it out on paper? So the lower bout square inch was directly related to scaling, because it's pretty amazing that it's so on a direct line like that.
Well, I could have fudged the data. And honestly, when in terms of string pull, I just had the strings that I had to work with, I mean, I think, for example, in the nylon string guitar, you could have higher tension strings or lower tension strings. But because it seemed so simple, that led me to try to be probably too bold and make a general model. I should say, though, that this is, I would call the model is semi-empirical. In other words, I use actual measurements in some cases to try to predict what the model would be. But I also, it's very important to use the actual physical geometry, the saddle height and scale length and top radius, and if you can, the average stiffness of the top itself, which can be measured, okay, to really give you more of a sense of this is not a astrophysics kind of model, okay, but it's a combination, it's rooted in reality in terms of the physical measurements that you make and comparisons with actual instruments that I measured. Did that?
Yep. I can't wait to get the book.
Well, go slow. It probably took me 30 years to write it. So there's a lot of stuff in there. After the top deflection model, I think the next thing that was very interesting is, oh, and I should say before we go too much further, I don't have many heroes, okay? But in terms of instrument making, I would have to put Graham Caldersmith, the late Graham Caldersmith from Australia, right at the very top. He is someone who did both violin family instruments and guitar family instruments. And he unselfishly shared in many, many publications the results of his work, his physics approach, his acoustics approach toward instrument making. And he's just a giant. There's one, if you have access to it, it's now, I think, available online. It sounds crazy, but it's the Journal of Catgut Acoustics. You need to do a Google search for it, Journal of Catgut Acoustics. And some California university has taken all of the old issues, digitized them, and put them online. So it'd be great to follow one. Let's see.
I think Graham
it's called
too.
Graham Caldersmith, and Low Range Guitar Function and Design. Graham Caldersmith, Low Range Guitar Function and Design is one article. Okay. And another one is Physics at the Workbench of the Luthier, again by Graham Caldersmith. Super guy. Just wow.
I think some of his articles might be archived in the Guild of American Luthiers also. Like if there's any kind of search function or in the big red books, I think some of his stuff regarding it in relationship to what you're talking about is in there.
With the GAL, I was a member for many, many years, and I am not now. And I went to their website to try to download an article, and you can't do it without paying. So that's a little bit of a downer, actually, I thought. So I don't know how to get around it, except if you, again, go to this digital archive for the Catgut Acoustical Society and just
it's called
Google
Journal.
Caldersmith. The journal is Journal of the Catgut Acoustical Society.
Okay.
It's really hilarious. I mean, it was created, I believe, by the late Carleen Hutchins, who knew more practically about violin and violin theory than anybody on the planet. And this Catgut Acoustical Society had a very high level in terms of the quality of the articles, even though it was put out on a Mimeo machine. If you can go back in and get some of those articles by Graham, they're just fabulous.
Yeah, I found a page with it, but I don't see the articles yet. You said Carleen Hutchins, right?
Yes.
Yeah, okay. I put a link to it in the chat of what I found, and I'll dig a little bit deeper and pass that on to Ian so he can include that in.
Well, the reason I mentioned that is, again, in that Journal of Guitar Acoustics, which really has disappeared from the planet, unfortunately, there is a very interesting article by a man named Jürgen Meyer. And I took all of the data from that article and again put it on both my website and in the book. This is chapter 6 in the book, called Resonance Coupling. Really, really, I mean, I can't go into it very much at this point. But if you're interested in how the air resonance, the Helmholtz resonance, the resonance of the top and the back under different circumstances of stiffness of back and sides, this chapter 6, trying to appreciate the work that Jürgen did in terms of the thousands of measurements that he made under all these different circumstances. It's a really interesting piece of work he did, and I just tried to honor it by putting these things into the book and on the website. Okay.
Thanks for grabbing that, Bo. So everybody, as Dave is talking about this stuff, I'm on Google and I'm trying to find everything. So I'll put links to it in the chat. So if you all are looking for what Dave is talking about, Bo just got the Caldersmith papers on Amazon, and I stuck the CACA Acoustical Society stuff in the chat as well.
Oh, thanks very much. That's
yeah.
great. So the next thing, go ahead, shoot.
Chapter 2 in that Caldersmith papers book is one of the articles you mentioned in the cat gut thing. So it's probably all there if you want a physical copy.
I think Graham's wife, did she not put out a book honoring his legacy? Is that the book you're talking about?
Yeah, I think it was more Graham McDonald. You probably know Graham.
Okay, sorry.
Yeah. He's another Aussie
sharing guy. Well, I always say, you know, behind every locked door is an empty room, you know. And people in the ukulele community have been hiding things that have been known for 100 years. So it's, well, anyway, moving right along.
Not to add any competition to this, but there's only 6 copies of this book left, and I'm buying one now. So the rest of you guys, if you want a copy of this, there's 5 left. Good luck. There's 37 people.
I got
in
a copy too.
Oh no.
Was this the Graham McDonald book?
This is the Caldersmith papers.
Oh, Caldersmith paper.
All right. Cool.
I'm sure they'll produce more. I mean, you know, what happens to me is after I have what I call the Dalia effect, where I sold a year's worth of books in 2 weeks and frantically rushed off to Office Depot to create more and get more flash drives and things. They'll make more, I'm sure. Well, okay. Dragging you, kicking and screaming into chapter 7. This is calculating neck deflection. And again, there's another spreadsheet, but you can put different things into the spreadsheet in terms of a neck insert of different properties and so forth and so on. Actually, the neck insert is in the neutral axis, so it doesn't necessarily add to the neck stiffness so much as, for example, the graphite carbon epoxy rod. It resists flow of materials. So it's really, I don't know if you can use the word a passive stiffener, but if the neck starts to come up, this stuff doesn't flow or warp the way wood do over time. And yeah, there's a funny story when I started out doing this, and I was trying to buy some 3/8 square graphite carbon rod from someplace in Washington State. So I said, gosh, how stiff is this stuff? Oh man, it's really, really stiff. And so, wow, that's really to two significant figures, you know? Well, they gave no measurement. So what I ended up doing was basically putting it between two pieces of angle iron, putting a weight on it and measuring the deflection so that I could calculate Young's modulus. And yes, it was really, really stiff, but it turns out that hardware store aluminum rod had the same stiffness. So that may not be true for modern graphite carbon epoxy, which is probably more stiff, but it's easy to measure and put in the neck deflection model. In fact, I ended up using aluminum rod instead of the graphite carbon because when you sand the graphite carbon, all those little really nasty nanoparticles go into the air, and even if you're wearing a mask, it's a little something to worry about. So, yeah. The only thing about the aluminum, though, someone else has mentioned, though, that the aluminum has different acoustical properties than the graphite carbon. And if you believe that the neck really affects the acoustics of the instrument, which it might do more so for a solid body instrument than a hollow body, it's something to think about swapping the aluminum back and forth with the graphite carbon. Yeah. Well then, let's see.
Dave, are you still building books at the moment, or did you retire?
20 years ago, no, is when I stopped about that time, because it was, you know, when you have a day where you begin each day undoing an hour and a half or an hour and a half the mistakes of the previous day, it's kind of bad for mental health. And I thought, well, leave at the top. You know, I was actually back ordered for 7 years. And I know it was almost like having a real job, right?
I learned about you through Chuck Moore.
Oh, yes. Actually, Chuck uses the compliance top method. He may not say so, but if you go over to his house and beat him up a little bit, you know. Yeah, there's a surprising number of closet compliance map users out there. Yeah, Chuck, oh my God, his inlays are just like, holy smokes, right? Well, anyway, I guess the other thing about the book is that I kind of became interested in too many different things about instrument making and so forth. And that's kind of what led to chapter 9. And so bridge sizes, gluing of bridge plates, things like that. It turns out that the glues for bridges often have really, really good shear characteristics. Really good. But where they fail is the peel strength. Peel strength. And so that's why it's so important, because you've got this lever arm, right? Okay. And the lever arm is trying to lift the back of the bridge up. And that's where the peel strength, the peel strength of the glue really comes into it. And I think that's why Gore wants to have no more than a 2-degree angle, although I have no idea how you measure that, a 2-degree rotation angle of the bridge. But that's also why in your compliance mapping, the area between the bridge and the sound hole becomes very important in terms of how stiff that is without compromising tonal quality, okay? Because you'd like to reduce that rotation so that you don't have the peel strength of the glue come into effect very much, yeah? And so using the compliance maps of successful instruments where that didn't happen is a really good guide along with other things to help you in your building. Let's see, temperature and humidity, there's a lot of graphs and stuff in there, but then I go into further on in there, braces, brace shape, brace, and then the effects of putting composites into braces. Usually when an engineer who's new to instrument making comes in, the first thing he says is, well, I don't know why you guys don't all use composite braces for the tops. You know, it's so much lighter and stiffer and so forth and so on. And people gently tell him that you really need to kind of whittle away at the braces to get the final product that you want. And so grinding your way through that graphite carbon epoxy that you put in the center of each brace is a little difficult and hazardous. So anyway, it's a lot of stuff to worry about in terms of calculation of the different kinds of braces. But again, if you put your braces in when the top is arched and when the back is arched, and you use a mold, which I'm sure you've created with your 3D cutter, Tom.
Hold on, I'll be right back.
Yeah, sure. Actually, I found mine in the rubbish bin behind a countertop manufacturer that had just the right curvature. So I did take a kind of a shortcut there. Oh, he's back. Oh my God.
So I have this.
Oh.
And what this is I have a radius built into this, whatever the radius of my top is. And like I have my frequencies on here for the different guitars I've made.
Right.
And so rather like I'll put this in with my braces on it. I use this one for my back. So like that's what I was asking earlier about you having it attached to the sides, because I do all my measurements for my top with it glued to the sides. But for my back, I'll do deflection using this guy. And it's just 3-ply MDF, but I do have the radius of my back built into it. So when I clamp it down, it's got reliefs in it for my back braces and everything, but I'll clamp it down and it tensions the back. And then that way it kind of simulates as if the back was stuck to the sides. So I have made these for like tops too. But I usually just use it on the sides for the most part. But yeah, so use the CNC for this, cut the parts out. And then as I do a guitar, I just use the same jig every single time. And then take my frequencies, my measurements off of this. And it works great. Ben, who's in here somewhere, I think, he also does the same thing, but for arch tops. So he has a set of this, but he's not putting braces on the back of his arch top, but he's using it, doing the same thing that you're talking about, checking the deflection, but without any braces, just by in the white carving in places and seeing how that changes how much it's deflecting. And then he'll also, besides doing any sort of mapping for his thickness, he'll pay attention to that as well. So he does the same thing. I don't know if I think he's in here. He's probably listening. I don't know if he's in his shop right now, but he could show you something similar to that. But yeah, all the same stuff, and the CNC is great for making that.
I have a quick question. Can you guys hear me?
Yeah,
Sure. Go.
Kind of silly one, but regarding the arch of the top, you said a 30-foot arch would give you free stiffness. I've been doing like a 15-foot full dome on my newer guitars, and it works. It seems to work well, but I just wonder, would you have any ideas about that? Is it too much of a good thing, or would you have? I don't really perceive an acoustic difference, but
A 15-foot arch? Is that for the top or the back?
for the top.
Wow. It seems this is a quote flat top instrument.
I've been doing it on classical guitars currently, but
okay.
I use an adjustable neck joint, so my neck geometry doesn't really intersect with the top, so it doesn't. So that eliminates a complication because I don't think you could do it with a regular neck joint. And as to why I started doing it, I can't even remember, but it was to solve a problem. I can't remember what the problem was, but it's solved.
Oh, excellent. Right. Well, by free stiffness, I meant that if you're pushing down on an arch, it's going to have some resistance. And what I never did, but of course continued to think about, was make a simple jig where you have a flat sheet of wood of typical top thickness or whatever, and a set of sides that you can bring together slowly with clamps, so that you very, very slowly increase the arch of the top, and then simply measure the stiffness, measure the deflection with a little load and a dial indicator, and see just how much effective stiffness actually was involved with the arch itself. Yeah.
Mm-hmm.
And because, I mean, some people actually make a parallel arch in the top, and others make a bowl arch. And by parallel to the fretboard, so it's like a half a tube.
Mm-hmm.
But I think for everything, it's all what you're trying to do is to reduce bridge rotation, right, along with the bracing, without having to put so much mass into the top with the bracing itself. Does that seem right?
Yeah. I guess, I guess if we're coming from boat building, when they would make something out of plywood, which is like, can really only bend in one direction, they would call it, I think, torturing, which is when you're bending wood in two directions. So I'm using a full dome, and I guess, sometimes I wonder what the longevity would be, because I'm bending the wood into bending a flat piece of wood into a circular shape, and it gives me some concern, but it seems to work well thus far. So I'm continuing to do it.
Well, my suggestion on that is that if you're bending it to the point where it's completely reversible, you're bending it to the point at which the wood would bend back to its original level if the thing were released. In other words, you're in the elastic rather than the plastic deformation load, then I think it's fine. I mean,
meaning I'm not breaking you're saying I'm not breaking fibers, the wood is returning to its original.
That would be my suggestion.
Yeah, I think I'm pretty far from that being an issue, but that's a really interesting way to think about it. Thank you.
Yeah, well, guesses are cheap, right?
Call me in 5 years and see if they all break.
Well, I think what would be interesting, and I'm sorry to beat a dead horse, but I really, with this compliance mapping, it would be very interesting to me to see if there were measurements of older guitars which people felt were still successful. I mean, they were historically successful, but somebody just basically played the snot out of them forever, and then they really got tired after a while, but ones that were still successful in terms of the image of the player, 5 years, 10 years, 20 years, that would be wonderful to see those things, because again, the compliance mapping, it's not a silver bullet, or there's a brand new shiny object or whatever, but it's just, I think, a really useful tool that you can use along with other things. For if you go and you tune to a particular frequency, things like that, and then afterwards, spend another 20 minutes or so making the map of that instrument that you can refer back to later. I mean, yeah. And if you make something that seems a little tight and doesn't break in after 6 or 8 months, what do you have? You have that stiffness map that you can refer to, right? And so, okay, fine, reach in the sound hole and maybe take a few mils off one place or another, remeasure, and see what that does to the instrument. Because sometimes that little break point is just so small in terms of taking that stuff off, because remember the stiffness of the braces goes as the cube of the height. So taking off just a little might make that just little difference that would just bring it alive. And then you'll have the map to get a sense of one more piece of information off to the side as to why it did really work well. Okay, that's great. Save the map. It's a little stiff. Oh, well, maybe bring it up a little. Oh, it deformed more than I thought. Whoop. Why is that map under the same circumstances that I build? Was that really the reason that it cratered a little bit more to your satisfaction than to your like? Anyway.
Thank you.
Never met a map I didn't like, except when things went wrong. So then I guess we're pretty near the end. Go bars. I think go bars are really fun. It turns out that, and I'm going to see if I can do this without destroying anything. It turns out that when you press down on a go bar, from the very first point at which it begins to bend and almost entirely thereafter, the downward pressure is exactly the same. What? I mean, okay, so I'm going to see if I can show this.
Zach, you just did this recently, right?
Pardon me?
Yeah, I just did a video about this recently. Yeah.
I'm going to get this. Well, what I'm trying to do takes two people, unsurprisingly.
Well, we can,
But I think I can do this. It'll take just a second.
yeah, we have time.
Crap.
So I think everybody, while Dave is doing this, y'all have lots of really cool guitars coming through your shop. So y'all should be making this this top compliance jig and taking some measurements. Where's Spencer Deaton in all of this? Of all people, like Spencer would be all over this.
Spencer
Okay.
was here.
Is he? Is he still in here?
Okay.
Oh, I'd love
Dramatic
to dive
moment.
into this, but I got to pay my mortgage at the same time and do a bunch of stuff.
Okay, so I'm going to press down on this, and it's going to go to about 9 pounds, and you can't see it, but the fiberglass rod is bending and bending and bending, and the weight stays at 9 pounds. And that means to me, when you're making your go bar deck, as long as the rod bends just a little, it's the same as having it bend a huge amount.
Oh, I see.
Right? It's
And
stuck there at 9. You can't see how much the rod is bending, unfortunately, but let's see if I can. Oh.
There we go.
Well, maybe.
Yeah, perfect.
See, this is when I want arms that are 8 feet long.
That's perfect for the view.
Ah, crap. Well, okay, I don't know. This is bending. You can see a bend in it. Okay, and it's still at 9 pounds. More or less.
David, is that poplar dowel from Home Depot?
Is that what? This is
Is that-
fiberglass.
Oh, it's fiberglass. Okay.
Yeah, it's really cool. A quarter of an inch square, and I got it a long time ago from a kite manufacturer.
Oh, I like the sound of
In
this.
other words, really cheap compared to places who will not be mentioned.
Oh,
And unsurprisingly, there's a spreadsheet in the book that goes on and on about fiberglass or any kind of wood that you want to use for your braces and stuff like that. It's well, are you tired of me at this point?
no.
No, this is amazing.
What I can try and do also is do another little setup for the top deflection. I think I did that very briefly
Wow.
before.
Before we move on from the go bars, anybody looking for really good go bars that are going to be really expensive? Sailing battens work fantastic. So they're for racing sailboats, and they're super strong in terms of they don't break like a wooden one would, but they're also flexible enough and they don't wear down. But they make them like rectangular shaped. So it's a little bit easier to use than like, because Paul mentioned like driveway markers. But sailing battens, they work fantastic. The only bad thing is that they're super expensive. But once you have a set, you have it. So, all right, Dave, you're good. Go ahead.
I have something to add to that if it's not as far as like a source for those. I order they're under the brand name Master Halco. They're called tension bars, and they're a chain link fence supply. Home Depot sells them, and they're like $2.50 each or something.
You want to put that in the chat, and I'll put a link in.
Are they made out of fiberglass?
Yeah, they're fiberglass. Yeah, I can
cool.
put a link in.
Cool.
Zach, I was always trying to find the green garden stakes that Sergey de Jong used, the rectangular ones, but I could never find them in the States. I don't know if you know where to get them. Do you know what I'm talking about?
Yeah, the garden supply.
Yeah, I think they're the same thing.
Is that what those were? I thought they were garden stakes. They're for fiberglass or for chain link fences.
Yeah, that's what I've bought. They're the exact same dimensions and they're fiberglass. So I don't know.
Okay, cool. Yeah.
Okay, now everybody needs to get out your letter scale, right?
Yes.
And hand
Yes.
protection so that you don't pierce your hand doing science.
One last thing I boxed up one of my guitars with those fiber rods, and we had two different lengths, and I used the wrong length, and it was like they all popped at once, and it was like a nuke went off. Like I think I still have red marks from where I was hit. It was so bad. Okay, you're good, Dave. Go ahead.
Yeah, but don't forget now, for the Go Bar deck, you want to adjust the height of the deck so that basically when you have the rod on the braces, it only goes down about half an inch.
Yeah. Yeah.
Because anything more than that won't make it any
stronger. Yeah.
Apply more pressure.
Mm-hmm.
And it has to be a little bit safer and all around.
So what is a good poundage for gluing braces on?
Well, honestly, I thought this 8 or 9 pounds was plenty. And you have this little forest of braces underneath the Go Bar deck. I made mine fairly long, really long threaded rod, so that just a sec.
I think I've been bracing way too hard.
Yeah, all of mine are about a yard long or about a meter long, which sounds like crazy for the length of these things. But again, I suppose you could have less braces and higher pressure, but on the other hand, you don't want to deform the brace by having too much pressure on it. So 8 or 9 pounds never seem to have any effect or like denting the braces or anything like that. And with that low pressure, they're very easy to put on and take off also. So that would be my nickel, is the yard-long quarter-inch fiberglass. But it would be fun to try the garden stakes and just look at, get out your postal scale and your hand protector and see just how much pressure they apply.
I got 3/16
Yeah, there we are.
rod from a kite maker as well.
Yeah.
And I just put it on my scale. It's 5 pounds. So
Cool.
I do notice a difference. Like I would like a little bit more. Like 7 pounds, I'd be happy. 9 is probably sufficient, more than enough.
Okay, there's an easy fix. Make it
Okay.
shorter. Make it shorter.
Make it shorter.
I can send you the form. It's Euler, E-U-L-E-R, from around 16 or 1700. You calculated column bending and column stiffness. If you make it shorter, it's stiffer.
But then I'm gonna hit my head on my go bar deck.
There's no pleasing you.
But then I'll have to dig a
Take some
hole
head shortener,
in the go bar
Trevor.
deck. What's
Well,
that?
actually, it really is so, though. If you make it shorter, it is stiffer, although, and you can calculate it. I can send you the spreadsheet if you give me your email.
Sure, why the heck not?
I can send that
And
to
I'm not
you,
sure if it's a
Dave.
linear relationship or a square or whatever. But it would be very easy to give you
Tom, could you look
exactly the
that up?
poundage that you like.
Euler's column deformation,
Yeah.
is
How
that
do you
what it
spell
is?
that, Dave?
EU. I think it's-
E-U-L-E-R.
Yeah.
E-U-L-E-R. Column.
Use fiberglass, the driveway stakes. I'm getting 19 pounds, so I don't know if that's too much or too little. But
They're pretty rigid. They're pretty rigid.
yeah, and they're super cheap. I think it's like
I found those driveway stakes in 2 different places in Home Depot, and the 2 different places had different stiffnesses.
you can check the tap tone if you have a tuner with you. So.
Yeah.
I thought you were gonna say there are different prices, so you just took them from the lower
No.
price.
So no, now what you need to do is take your postal scale to the hardware store.
They have all the stuff to make a go bar deck too, so you might as well just set that up.
I gotta share with you a dumb idea I had, but I 3D printed some fittings for some turnbuckles, and I cut my driveway pole in half and then used the turnbuckle to make an infinitely variable go bar stick. So, oh boy, that was well received.
I think it's trying to picture it.
Oh, I got it around here somewhere. I don't know. It's just, imagine a turnbuckle in the middle of it, so you can turn it and you can dial in your tension of your go bar stick. It's mostly, I've got some top cracks coming up where I want to do top splines, and I want to be able to align the top and drop the top splines in. So yeah. And you can't, it's very difficult to get go bars to put out just the right amount of tension.
Oh, okay, I got it. Yeah, cool.
I'll send you a picture. I'll dig it up and send you a picture.
Okay. Well, and probably last but not least, here is a little picture of the compliance measuring setup. Again, this is pretty much exactly what's on my website here. And you have a cross piece here that goes from one edge to another edge, and it has a series of holes in it in the top. And this is the $10 dial indicator from, oh crap, well, I'm trying to remember the name of that inexpensive Harbor Freight. Yeah, Harbor Freight.
Classic.
And of course you can have it in mills or whatever you want. Then this is just a long rod here that's attached to a little threaded, bolt inside this. I love PVC. Okay, this PVC unit, and that in turn has a kind of a long foot on it. Did I completely?
Oh, you're
no?
out. Your iPad's having some
Okay,
focusing
there we are.
issues.
Yeah,
There we go.
Great.
Dave, if you go down to the camera thing, there's a way to turn off the tracking because it's trying to track your face.
Okay. Don't do that. Okay. So basically what I'm going to do is put a weight on this little pad on the, and what's happening is that the dial indicator moves. Okay, can everybody see that?
Yeah.
Okay, and what you like to do is to have, I just have a piece of maybe 2 or 2.5 inch diameter steel rod that will always be the same weight to put it on the little pad. And so this, basically what you do first is to press down on the little lever arm. And that, what that does is to make sure that you have the same return indicator, the return number on the dial indicator. And you also want to kind of look around and, look around and make sure that the dial indicator is not touching the little open kind of nut at the end of it. And you have a little piece of leather underneath, leather or rubber glued to, so you don't bung up the top. Okay. And so you will press on this a few times to make sure that it comes back to the same spot. Put the weight on and do the same thing again to make sure that this now comes back to the same spot with the weight on it. And as in all things, for the dial indicator, you want to have this in the mid-range of the dial indicator. You don't want to have it 0 at one end or at the other, because what you're looking at is differences. And so the differences really are what you're measuring. So this would be, I guess, about 7 mil. And this would be about right for me for a top. This is a tenor sized ukulele, so this is about right. Although it doesn't have the bridge on it, it's about right for the high tension strings. And so, any questions about the device or anything? The process? It's.
I've seen similar devices, but without the arm, and they just put the weight on top of the micrometer on the very top of the micrometer. And I'm just wondering what the advantage is of having the arm the way you have it, if that makes sense.
First of all, I never thought of it. So that's the simplest. And I couldn't appreciate, I didn't think that the dial indicator would be strong enough to deal with that mass pushing down on it from the top, because it's, I mean, we can try it, of course. I mean, but I have not built a special plywood frame. I think Nicoletti does something like that, or other folks do.
Maybe Gore did it somewhere along the line, I think, in the past, or some people who like Gore.
The system that I used, there was 2 of them that I used, and one of them was very similar to your setup, but the weight was, it was shaped with a cutout in it, so you could place it right on the top, and then it would go around the micrometer. But then the other one where the weight went on top, like it was gargantuan, and we called it the Eye of Sauron, and it was super extra. So like I've seen it, like I've had the way that I checked all the deflections on my tops, because since my guitar is so small, I had a hard time with frequencies, because it's smaller. It inherently has a higher frequency. And the same principle that Dave talked about in making the rod shorter, when you make your guitar smaller, it also makes it a lot stiffer. So I ended up graduating my tops. So I thinned out the rim around the outside of my top, which on this one that's sitting next to me was not a great idea, because I ended up cracking it and then thinning it out more. But I used the weight right on the top around the actual piece. But my back was glued on when I realized that it was way too stiff or way too high in frequency. So I was checking my deflection to make sure that the what Dave is describing with the bellying and the torque of the bridge, I wasn't going to push the limit so far that my top was going to be screwed. But then I cracked the top, gluing the bridge on. So then I thinned it out, and then I lost all of that stiffness in my top, not in my braces. And now I have a guitar that it has a pretty severe belly behind the bridge. But that system just clamped right to, and it's the same idea as what Dave is using, just without the lever. But the big one where we were putting it on top, it just requires, in order to get a weight to sit on top of that micrometer, you need a bigger platform for it to sit on. So I always gravitated more towards the system that Dave used. Mine just clamped on. So I think Ben has, again, I keep mentioning Ben having it, but I think he's popping in and out. Oh no, he's in here, but he has something very similar. Let me see if he can pop on. But that's what
well, for me, the take-home message is that however you do it, I'm 100% okay with. This was just something I came up with that, was inexpensive, and I got it worked. I don't know, but 20 years have passed.
Yeah.
What's the weight on that you're using?
It's about 2 pounds.
2 pounds, okay.
And to calibrate it, what I do is to basically I take everything off, and I use just a regular kitchen scale, and I put the little end of the lever arm on the middle of the scale, and then and you want to have the lever arm horizontal when you do that. So whether you have to move this up and down this column that I have the lever arm in, but as long as the lever arm is horizontal, and you have this little end piece in the middle of the scale, the kitchen scale, then you put the weight on it, and basically the effective weight right where the dial indicator is.
Hello everyone.
Giuliano.
Hey, Giuliano.
Hello.
Hi Dave. And I think it's a nice system that you have, and as you say, as long as the lever is horizontal, the deflection is usually very small, so it shouldn't be affecting, in fact, the reading of the weight that you are using. It's a good system. It's a little bit more, it's a little bit more complicated than just using a jig and a micrometer with a weight on the top, but it's a nice system. I guess that you designed that system because you wanted to move around over the soundboard. For that purpose, for that purpose, it's of course very well engineered. Actually, for the purpose of measuring monopole parameter, you don't need to move around. You just need to know the overall compliance of the main monopole, and so you just don't need it. But it's a nice system.
Well, the thing about measuring the overall compliance of the main monopole, which I think that's a great measurement, okay, but the compliance mapping tells you so much more in terms of the overall stiffness of the top, and in retrospect lets you perhaps understand why a top was perhaps too stiff, or at the correct optimum, or if it bellied a little bit or not, then you could adjust your instruments later on so that they were a little more resistant to that plastic deformation of the top. So, I don't think the end result is, I don't think that the compliance map is the end result, but rather a useful parallel tool.
Of course. It's a very interesting system. From my point of view, it all comes down to what you are looking for with any kind of measurement should just give you some answer to the questions. So what is the main problem that you want to solve? What is your approach to the building? Of course, mapping the compliance, it's very interesting. As you just say, it gives you a clear idea of how different parts of bracing systems and the soundboard interact in designing the overall compliance. And that's, of course, it's interesting. From my point of view, it is something that I don't suggest as a starting point for the builder that begins to explore the technicalities of the acoustic instruments, because I believe that it is maybe a next step, a next level, considering that you have the main monopoles, the first resonances that are maybe the most important, and then you have higher modes. Frequency of the higher modes are related to several parameters, not just the compliance of the board. First, the first parameter is dimensions of the board, then the shape of the board, of course, the way the waist is designed. I mean, I get what you're looking, but what you have a very specific interest in the engineering of the instruments, from the way the soundboard interact with the strings and the way the soundboard deflect. It's really an engineering and mechanical approach. It's very interesting, of course.
David, can I interrupt really quick, Giuliano?
Sure.
Yeah, sure.
David, can you give us just an anecdote or a for instance of how you use that information in a build, or do you have a specific thing you were maybe having a struggle with your instruments, or had an aha moment where you're like, I know I can do this and get a different result using that information?
Well, what happened is I started to try to do different kinds of approaches for making a top that seemed to, making an instrument that sounded nice, but in the end, they didn't exactly, they weren't so long lasting in terms of their looks. There was the bellying and dipping and things. I mean, the instrument sounded like a cannon, okay? But really, it could have been much better. And so what I ended up doing was just trying different compliance maps. And then I finally ended up with what I felt, and I think I showed this in the book, and it's how it led to the predictive model for compliance mapping. I found compliance maps which worked for my 4-string tenors. I think that was the best instruments I ever made with my 4-string tenors. And at that point, for all of the rest of them, I only made instruments at the top according to the compliance map. Okay, so then I measured the top primary frequency, and then I took the back and measured it such that it was 2/3 of that frequency as a free plate, so that when I put the back on, the back, the top, and the air resonance all made a coupled oscillator. So what I wanted to try to do was, when the back frequency was within a semitone or so, then they coupled such that I didn't have the dead spot that normally comes with just the primary frequency from the top. So you can go, down the fretboard and easily see where you have that dead spot, okay? And again, coupling the back with the top reduced that to almost nothing. And there's a very interesting way that someone told me about, I can share with you just for a minute. And it gives you a sense of how much the back and the front are coupled. So just a sec. So here's one of my concert ukuleles from long ago, from, oh my goodness, 15 or 20 years ago. And what I'm going to do is just tap on the top. You can hear that okay?
Yep.
Now I'm going to tap on it with the back muffled.
Zoom
Oh.
is starting to.
Yeah,
The
Zoom.
greater the difference between those two, the more coupling the top and the back have. Really cool, right? So simple. Adjusting it is hard, but recognizing it is pretty nifty. Yeah.
And that's why you see so many classical guitar players. They always look super uncomfortable when they play them because they're trying to not have their body up against the back of that instrument as they're playing it. Yeah.
I think that's the goal in terms of if the instrument was built such that they deliberately tried to couple the back and the front to reduce that dead spot because of that primary influence of the, what is it, T11 or whatever the first top vibrational mode is. So, and that's why, of course, unlike steel string guitars, many of the classical guitar tops, backs rather, are very lightly braced in comparison. I mean, I think the last 15 or 20 ukuleles that I made, the back braces never even reached the linings. I just left them as free so that I could actually try to tune such that it got the frequency I wanted and the glitter pattern was a circle all the way around the perimeter.
You
That was
you ever tempted to make a spruce back guitar?
I'm sorry, what?
I was just wondering if anybody's ever made a spruce back guitar going for that ultimate.
Dick Boak made an entire guitar out of spruce. He made
Did he
he
really?
makes a bunch of them. Yeah, he constantly makes them. Neck and
Okay.
everything. Yeah.
Oh my god.
Sergey did that as well.
Who?
Sergey made a guitar out of
Oh,
Port
yeah.
Orford cedar.
Is
too.
it just like a cloud of
yeah.
sound around you or something? Or?
We did a guitar entirely out of Polonia once, and I thought it was gonna fly away.
Yeah.
It was like it felt like balsa. The entire guitar just felt like balsa.
Bo Hannum's got a story about building instruments out of that.
Oh, we
which-
did the same thing. So we were
Yeah.
part of the same adventure there.
Did Jimmy Carter
Yeah, the
do
Jimmy
you
Carter
dirty
would.
do you dirty too?
With the Kiss signed strap pick guards.
All right.
Yeah.
Right. One, Tom.
What was that?
Did you build the Brian Gallup Polonia?
Yeah, we did that in 4 days. So that was an adventure. Yeah. It's cool wood though. Definitely great for like tops and stuff.
Yeah, I've still got some of Carter's wood over there. I was supposed to send it back, but I never did.
Beautiful tops.
Well, anyway, it worked out for me that I just ended up making all of the instruments according to a compliance map and then adjusted the back relative to whatever frequency the top was. And I don't know, people liked them, you know.
That's the bottom
25
line.
years ago, or 20 years ago, they were selling for 3,500. And they seem to have kept their value. So
Yeah.
That's what we like.
And they're out there making music. That's the important part. Well, cool. Should we schedule the next one?
oh my
Advanced
goodness.
Lecture?
Has everybody had as much fun as they could stand?
I think
This was
I think
amazing.
This was a really good. This was fun.
That was helpful.
Like-
Thank you. Sorry.
Thank you, David.
Yeah, I really
Yeah,
enjoyed
my
this.
pleasure. Hey, thanks for joining
Actually,
in.
everybody take a second and unmute and thank David for sharing his time with us today.
Thanks,
And,
Dave.
David.
Thank you.
David, thank you.
Thank you, David.
Thank you, David.
And I would like to get you back to do some more talking at some point. Like this was fun. Yeah. Anyway, thanks everybody. I'm gonna stop the recording so you all can speak freely again. And the Luth Long is in full